In the last couple of videos, we first figured out the total variation in these 9 data points right here, and we got that to be 30. That's our total sum of squares. And we asked ourselves how much of that variation is due to variation within each of these groups versus variation between the groups themselves. So for the variation within the groups, we had our sum of squares within, and there we got 6. And then the balance of this 30, there's no units here, the balance of this variation came from variation between the groups. And we actually calculated it. And we got 24. What I want to do in this video is actually use this type of information, essentially these statistics we've calculated, to do some inferential statistics, to come to some type of conclusion, or maybe not to come to some type of conclusion. And what I want to do is just to put some context around these groups. We've just been dealing with them in the abstract right now, but you can imagine that these are kind of the results of some type of experiment. Let's say that I gave 3 different types of pills or 3 different types of food to people taking a test. And these are the scores on the test. So this is food 1. This is food 1. This is food 2. This is food 2. And then this right over here is food 3. Food 3. And I want to figure out if does the type of food that people take going into the test, does it really affect their scores? Are the differences in these scores, if you look at these means, it looks like they perform best in group 3, then in group 2, or then in group 1. But is that difference purely random chance? Or can I be pretty confident that it's due to actual differences in the population means of all of the people who would ever take food 3 versus food 2 versus food 1? What I want to do is say, so my question here is, are the means, the true population means the same? So if the true population means, this is a sample mean just based on 3 samples. But if I knew the true population mean, so my question is the mean of the population of people taking food 1 equal to the mean of food 2? Obviously, I'll never be able to give that food to every human being that could ever live and then make them all take an exam. But we're trying to get a sense of there is some true mean there. It's just not really measurable. And so my question is this equal to this equal to the mean 3, the true population mean 3. And my question is, are these equal? Is because if they're not equal, then that means that the food actually, the different foods that you get actually do have some type of impact on how people perform on a test. So let's do a little bit of a hypothesis test here. So let's say that my null hypothesis, is that the means are the same, or food doesn't make a difference. Food doesn't make a difference. The food doesn't make a difference, and that my alternate hypothesis is that it does. It does. And a way of thinking about this a little quantitatively is that if it doesn't make a difference, the true population means of the groups will be the same. So that means the true population mean of the group that took food 1 will be the same as the group that took food 2, which will be the same as the group that took food 3. If our alternate hypothesis is correct, then these means will not all be the same. So how can we test this hypothesis? So what we're going to do, we're going to assume the null hypothesis. This is what we always do in our hypothesis testing. We're going to assume our null hypothesis, and then essentially figure out what are the chances of getting a certain statistic this extreme. And I haven't even defined what that statistic are. So we're going to assume our null hypothesis, and then we're going to come up with a statistic called the F statistic. So our F statistic, which has an F distribution. And we won't go in real deep into the details of the F distribution, but you can already start to think of it as a ratio of 2 chi-squared distributions that may or may not have different degrees of freedom. Our F statistic is going to be the ratio of our sum of squares between the samples. So it's going to be our total sum of squares between, divided by our degrees of freedom between. And sometimes this is called the mean squares between MSB. Either way, it's going to be that divided by the sum of squares within. So that's what I had done up here. The sum of squares within in blue, divided by the sum of squares within, sum of squares within divided by the degrees of freedom of the sum of squares within. And that was m times n minus 1. Now, let's just think about what this is doing right here. If this number, if the numerator is much larger than the denominator, if it's much larger than the denominator, then what that tells us is that the variation in this data is due mostly to the differences between the actual means, and it's due less to the actual variation within the means. That's if this numerator is much bigger than this denominator over here. So that would make us believe, that should make us believe, that there is a difference in the true population mean. So if this number is really big, it should tell us that there's a lower probability that our null hypothesis is correct. If this number is really small, let's say that this is larger. Let's say that our denominator is larger. That means that our variation within each sample makes up more of the total variation than our variation between the samples. So that means that our variation within each of these samples is a bigger percentage of the total variation versus the variation between the samples. So that would make us believe that, hey, any difference that we actually see in the means is probably just random. And that would make it maybe a little harder to reject our null hypothesis. So let's just actually calculate it for this. So in this case, our sum of squares between, we calculated over here was 24. 24, and we had 2 degrees of freedom. And our sum of squares within was 6, and we had how many degrees of freedom? Our degrees of freedom there were also 6 degrees of freedom right over there. So this is going to be 24 divided by 2, which is 12 divided by 1. So our F statistic that we've calculated is going to be equal to 12. And this stands for Fisher, who is the biologist and statistician who came up with this. So our F statistic is going to be 12. And what we're going to see is this is a pretty high number. Now, one thing I forgot to mention, any hypothesis test, we need to have some type of significance level. And so let's say the significance level that we care about for our hypothesis test is 10%. Is 0.10, which means that if assuming the null hypothesis, there is less than a 10% chance of getting the result that we got, of getting this F statistic, then we will reject the null hypothesis. So what we want to do is figure out a critical F statistic value that getting that extreme of a value or greater is 10%. And if this is bigger than our critical F statistic value, then we're going to reject the null hypothesis. If it's less, we can't reject the null hypothesis. And so I'm not going to go a lot into the guts of the F statistic, but you can already appreciate that each of these sum of squares has a chi-square distribution. This has a chi-square distribution, and this has a different chi-square distribution. This is a chi-square distribution with 2 degrees of freedom. It's a chi-square distribution with, and we haven't normalized it and all of that, but roughly a chi-square distribution with 6 degrees of freedom. So the F statistic is actually the ratio, or the F distribution is the ratio of 2 chi-square distributions. And I got this. This is a screenshot from a professor's course at the UCLA. Hope they don't mind. I had to find an F table for us to look into. But this is what an F distribution looks like. And obviously, it's going to look different depending on the degrees of freedom of the numerator and the denominator. There's kind of 2 degrees of freedom to think about, the numerator's degree of freedom and the denominator's degree of freedom. But with that said, let's calculate the critical F statistic. The critical F statistic for alpha is equal to 0.10, and you're actually going to see different F tables for each different alpha, where our numerator degree of freedom is 2 and our denominator degree of freedom is 6. So this table that I got, this whole table is for an alpha, a significance level of 10%, or 0.10. And our numerator's degree of freedom was 2, and our denominator's degree of freedom is 6. So our critical F value is 3.46. So our critical F value is 3.46. So this right over here, this value right here is 3.46. The value that we got based on our data is much larger than that, way above it. It's going to have a very, very small p-value. The probability of getting something this extreme just by chance, assuming the null hypothesis, is very low. It's way bigger than our critical F statistic with the 10% significance level. So because of that, we can reject we can reject the null hypothesis, which leads us to believe that, you know what, there actually probably is a difference in the population means, which tells us there probably is a difference on the performance on an exam if you give them the different foods.